Hello, welcome to another video of the R series, and today we will be discussing linear regression using R. This presentation will cover the fundamentals, practical applications, and interpretations of linear regression models. So today what we're going to talk about is simple linear regressions. Linear regression is a fundamental statistical method which is used to predict the value of a dependent variable, which is y in our case, based on the value of an independent variable, which is x in this case. Um, it assumes a linear relationship between x and y, meaning that uh, y increases or decreases depending on x. Like if x increases by a unit, y will increase by a proportion of the unit of x, and so on. So the basic form of equation is y is approximately equal to b0 plus b1 multiplied by x, and b0 and b1 is sometimes also written as beta 0 plus beta 1, plus if you have more variables in the equation, in case of like multiple linear regression, then it would be b2 into x2 plus b3 into x3, and so on and so forth. So beta 0 here is the intercept. That's the value of y when x here is equal to 0, and b1 is the slope. So it's the rate at which y changes for each unit increase in x, as you can see here from this equation. Like just to get a visual aid for it, imagine a scatter plot with a straight line through the data points representing this relationship. So the line represents this line that will draw through the points of the scatter plot represents the best guess of the relationship between x and y. Um, so coming to the coefficients, beta 0 and beta 1 are essential for making predictions, and beta 0, like I told earlier, is the intercept, and beta 1 is the slope. So for example, if we are predicting, let's say, house prices, which will be y in this case, based on the square footage of an area, which would be x in this case. So beta 0 would be the predicted price of a house with 0 square footage, just a hypothetical point, and beta 1 would represent the increase in price for each additional square foot. So one thing, a few things to know when finding this line of best fit is something called RSS, which is the residual sum of square, and it is calculated as the sum of squares of the residual. So now what is the residual? Well, residuals are the differences between the observed value, which is the actual data points, and the values predicted by the model. And here is where another thing comes in called the least square criterion, which is the method of least squares, which is used to find the best fitting line, and which aims to make this best fitting line by finding the lowest uh, residual sum of squares. So what I mean is that the line that we draw through all these scatter plots um, should be the line which has the lowest value for RSS. This involves solving for coefficients that minimize the RSS, which again require calculus and specifically taking partial derivatives and setting them to zero. But all of this is out of our scope here. But what we need to know is that these two equations, beta 0 for finding beta 0 and beta 1 to minimize the least squares, is used to find the line of best fit. Um, Now coming to the practical application and like the use of the linear regression model. One aspect to keep in mind before even using the model is like the accuracy of the estimates, like how accurate are the coefficient estimates. And this is quite crucial because it defines how reliable the model is. So any regression line can be expressed as y equals a function of x plus epsilon, where epsilon represents the random error or noise in the data. So a linear function, if we assume that the function of x is a linear function, like I said earlier, how a linear function works, we use the linear regression equation y equals to beta 0 plus beta 1 into x to estimate the relationship between x and y. So just to give you an example, consider an ecological study where we are predicting the growth of plant species based on, let's say, the amount of sunlight it receives, which would be x. So the linear regression model kind of helps us quantify the relationship and make predictions about plant growth under different sunlight conditions. So this is where another concept of true versus estimated regression line comes in. So in practice, the true regression line, which is also called the population regression line, is usually unknown. So we estimate this population regression line using the least square line, which is called the LSL, which is again derived from the sample data. And the least square line is our best guess at the population regression line based on the available data. So it is not exactly the population regression line, but it is one of the least square lines that kind of helps us guess the estimate of the population regression line. And one thing to keep in mind when doing this kind of analysis, like using A to predict B, or assuming that A is almost equal to B, is something called unbiased estimator, which basically means is that how would I define unbiased? Well, an unbiased estimator means that the average estimate across many samples would be equal to the true parameter. So what I mean by that is if you have a multiple least square lines for multiple models, and then you find the average of all those estimates, and then the final least square line would be almost equal to the true uh, estimated regression line. Now, if you have infinite number of least square lines, then it would be exactly equal to the average of all those lines would be exactly equal to the population regression line. The least square estimates of for the coefficients again can be calculated using the same unbiased estimator approach, and you can use number of simulations and generations to prove that, okay, if you have generated a set of data and you have found the true regression line because you know the parameters, and then you use a number of uh, simulations to get different sorts of model that gives different least square lines, and then you average all those least square lines, you'll find that the true regression line would be very similar to the least square line. And this is where you might ask me, well, okay, what if we just have one sample? Like, how do we measure the accuracy of our coefficient estimate using just one sample? So, and this happens a lot, especially in ecological data, where you don't have the liberty to go on field and collect hundreds and hundreds of samples, or hundreds of sample that has a bigger sample space. So with with a single sample, we measure the accuracy of coefficient estimates using something called the standard error, and this helps us understand how much our estimates, which would be beta 0 and beta 1, might deviate from the true values of beta 0 and beta 1. So for the formula, the standard error of a slope estimate, which is b1, is inversely proportional to the spread of x. So you can see in this equation, and here this sigma is basically the standard deviation of the error. And just to interpret this equation, like a larger spread in x allows for more accurate estimation of the slope, because it provides more information about the relationship between x and y. So let's take, for example, if you just have two data points and then you draw a line through that, and that's your model. Basically, you just have two observations. Then the slope of that line would be very steep. However, if you keep on increasing the number of observations, which is basically x, increasing the spread of x, the slope would keep on becoming either be the same or decrease or increase, which would give us a better idea of the true association. Because just two observations would not give us a better idea of how the data is in its actual reality. So having more samples is always better. For example, just to give you an example, let's say the the sigma, which is basically the standard deviation of the errors, is 10, and the spread of x is 50. Then the standard error of beta 1 is nothing but 10 divided by root over square root over 50, which is approximately equal to 1.41. However, if you keep on increasing the um, the spread of x, like let's say if you make it 100, then it will become half. So the standard error you can see here is decreasing as the sample spread is increasing. So this is again something that tells us how much we can expect beta 1 to vary from sample to sample. And when we are dealing with this linear regression, we need to talk about something called assumptions. So um, not something called assumption, but we have a lot of assumptions when we are doing dealing with linear regression. So one of it is common variance. Like for the standard error formulas to be valid, like using standard error, if it needs to be valid, the error term for each observation should have the same variance. And this is something in statistical term known as homoscedasticity. It's really difficult for me to pronounce. Um, but when you're actually dealing with a large sample space, this is not always the case with actual observed data. But even if the assumption doesn't hold true, it does gives us a better idea of the relationship between x and y, especially if the relationship is linear. Another assumption that we need to keep in mind is uncorrelated errors. So the error term should be uncorrelated, meaning that the error for one observation should not depend on the error of another. This assumption, again, is known in statistical terms, is known as independence. And another assumption, which I haven't mentioned here, is called something called linearity. So the relationship between, like I told earlier, the relationship between the independent and dependent variables should be linear. This means that the change in the dependent variable is proportional to the change in the independent variable. It cannot be not proportional. So like I told, in terms of proportion, in terms of how many times does x increase, does y increase or decrease depending on every unit increase in x or every unit decrease in x. So there's another assumption, something called the normality of errors, where basically the error term should be normally distributed. So if you draw a histogram of all the error terms of all the observations, it should form kind of a bell-shaped curve, and this should especially be true when you're dealing with small sample sizes. So this is one assumption that needs to be adhered to, especially when dealing with linear regression. Um, so again, this assumption kind of allows us to make inferences about the population from our sample data. If this doesn't hold true, then it doesn't really make sense to draw assumption. So to draw a conclusion. And to do all of this, we have diagnostic tools. Thank God, we don't have to do it mathematically. We have diagnostic tools in R to deal with it, and we will deal with it a bit later in the video. But in practice, we use diagnostic tools such as the residual plots and the QQ plots to check these assumptions. So the residual plots helps us assess the, like I told earlier, the homoscedasticity and the linearity, while the QQ plot helps us check the normality of the error terms. Now coming to residual standard error, this is something very important because residual standard error can help us to know how accurate the model is, or how good the model is. Residual standard error is basically an estimate of the standard deviation of the error term epsilon. So it gives us a measure of the average amount that the observed value deviate from the true regression line. So to calculate that, again, you basically the residual sum of square is divided by the degrees of freedom, n minus 2, where, like here, the degree of freedom is n minus 2, where n is the number of observations and -2 because we have two parameters in this linear regression, which is the response variable and explanatory variable, and then taking the square root of it. So the formula is basically RSE equals to root over RSS by n minus 2, and then yeah, that's basically it. So how do you interpret it? Well, so a lower RSE indicates a better fit of the model to the data. However, RSE alone does not provide a complete picture of the model fit, because you might have a very low RSE, but you might be overfitting the data, and overfitting is a big problem that we have to deal with when especially dealing with ecological data. And again, about which I will come to later in different videos, all about presumptions of data, all about biasness that uh, we can in like unknowingly introduced in our analyses. Example of just our RSC would be if, let's say, the residual sum of square RSS is 200 and we have let's say 50 observation, then RSA would be root over 200 by 48, because 50 minus 2 would be almost equal to 2.04. And this tells us that on average, this 2.04 tells us that on average, the observed values deviate from the regression line by about 2 units. So like the average, how much it is away from the true regression line is by 2 units. And then this again can be used to do hypothesis testing. So especially standard error is quite helpful in doing hypothesis testing, where what I mean by hypothesis testing is that you do a test between, you have a hypothesis, okay, like your hypothesis is that, okay, X affects Y, and then X affects Y is your alternative hypothesis, whereas the null hypothesis is that X does not affect Y. So in hypothesis, we often test whether the slope of the coefficient for X, which is beta 1, is significantly different from 0. Like the null hypothesis states that the slope is equal to 0, meaning that no linear relationship exists. So which again makes sense, because if we just talk about let's say, for example, you say there is a relationship between X and Y. However, for that means if there's a linear relationship, for every unit increase in X, there should also be a proportional increase or decrease in the value of Y. However, if beta 1, which is your slope, is 0, then there is no relation. No matter how many times you increase X, there won't be any changes in Y. However, if there is a relationship, then that won't stand true. So that's why in the null hypothesis, we say that beta 1 is equal to 0. And in the alternative hypothesis, we say that beta 1 is not equal to 0. Even if it's as less as 0.01, the coefficient is as less as 0.01, it still affects the value of Y for every unit increase or decrease in X. Again, we need to know something about the t statistics. So t statistic is again calculated. You can get the equation here, but it's basically t is equals to the slope minus 0 divided by the standard error of beta 1, and it measures, basically what it measures is how many standard deviation is the slope uh, away from 0. So a larger t statistics indicates that a higher likelihood that the slope is significantly different from 0, because it's more away from 0 in it. That's that, because if it's equal to 0, then there's no linear relationship. However, if it's not equal to 0, and if it has a higher t statistics, that means that it's further away from 0, which makes us more sure that, okay, there is a linear relationship between X and Y. For example, if beta 1 is equal to 0, if slope is 3 and the standard error of the slope is 1, let's say, like, then the t statistic would be 3 by 1, which would be equal to 3, and this would be compared to a critical value from the t distribution to determine signal. So you have this table called the t table, where uh, you if you know that your degrees of freedom, then you can use it to compare your t value to whatever the specific p value is. Now, speaking of p value, you might ask me, okay, what the hell is a p value? Well, p-value basically represents the probability of observing the data, assuming that the null hypothesis is true. So a small p-value, typically a p-value that is used is 0.05, suggests that we should reject the null hypothesis, indicating that the relationship between x and y is statistically significant. So, like, I'm now, it might be going above your head, but in practical terms, if a significant p-value, what it basically means is that the predictor variable x provides useful information for predicting the response of y. For example, in a study, let's say predicting plant growth based on sunlight, like how I told earlier, a low p-value would indicate that sunlight actually has a significant effect on the growth. Now, again, if we take another example, a scenario, if we have a p-value of 0.02 in this plant growth study, this means that there is only a 2% chance that the observed relationship is due to random variation. That means suggesting that there is a strong relationship between sunlight and growth. So if you do this test, if the p-value, like the p-value is 0.02, if you do this test for 100 number of times, only in 2%, two times of those 100 times, you will find that sunlight does not have a significant relationship with the plant growth. So that's basically about p-value. And then again, you just, when you use the t-table, you know your degrees of freedom, which is n minus 2 for simple linear regression. And then you know the value of your t statistics using the equations I have shown here earlier. Then you can just look for your look for your t statistics in the row which gives you your degrees of freedom, and then on the top you'll see the p-value. So if the p-value is less than 0.05, then you can say that, okay, there is a statistically significant relationship between x and y. Okay, now we were just talking about how to know that your estimates are accurate, and that's, again, you can use t-statistic, use p-values to do that. But how do you know that your model is accurate? Like I had spoken about earlier about RSE, right? Residual standard error. So to quantify, again, model accuracy, we can use that. Along with that, we also have something called the R-square statistics. Uh, but for now, let's first talk about residual standard error. The residual standard error indicates the average deviation of the observed value from the predicted value. So like I told earlier, um, while the R-square measure measures the proportion of variance in the response variable that is explained by the predictor variable. So how much of the variation in y is explained by x. So if you have to interpret R square, um, the R square statistics is also known as this term called what was the term? Coefficient of determination, and it ranges from 0 to 1, so it's always in proportion. So by that, what I mean is that it's between 0 to 100 percent, or 0 and 1, like any probability distribution. So if R square of 1, if there's an R square of 1, that indicates that the model fits perfectly to the data. While and R square of 2 indicates that there is no explanatory power. So for example, let's take the R square of 0. You have an R square of 0.8, which means that 80% of the variance in y, in your variable y, is explained by x. So if we just take again context, for just context, let's take the interpretation of R square. For example, in the field of physics, where data is often kind of, you can generate the data under controlled conditions, unlike biological scenarios, a high R square is expected. But if the R square is less, then they know, okay, the model is not that good. However, in contrast, in fields like ecology, where data is observational, you don't have the liberty to have standardized conditions on field. Although nowadays it is kind of becoming possible to a certain degree, but still, in most cases, it's not. The lower R square values are common, and that does not mean that our model is not proper. It's very context dependent, and it's important to consider that the context and the domain specific standard when kind of evaluating the R square. Uh, to give you an example calculation, if our model has an R square of 0.75, that means that 75% of the variation in the dependent variable can be explained by the independent variable, like the earlier example. Um, this is again typically considered a strong relationship, but the exact interpretation can vary depending on the field of study. Like I told, like in physics, it might be uh, not that good enough. However, in ecology, that, well, this is good enough, because you don't know all the variables um, that affect y. Um, so with that being said, I am ending the theoretical aspect of this linear regression, and feel free to kind of slow down the video and hear each and everything that I'm saying, because I know it's too much to take and I speak a bit fast. So to give a quite like a recap of the entire lecture, what we covered was the basic of linear regression, including estimation of the coefficient, their accuracy, hypothesis testing, and model evaluation using RSE and R2 statistic. Then we also discussed the assumptions lying linear regression and the significance of p-value. So if you have any questions, like, feel free to drop it on the comments. I'll get back to every one of you. And if you want any resources, extra resource, I'll link it in the description. And there's just two fantastic book that I'm using to base most of my uh, knowledge on, and like they say, building on the shoulder of giants. So now let's see how we can implement linear regression in R. We'll go through an example data set, fit a linear model, and then interpret the results. So we'll use a data set named lion noses, and it has column X and Y. However, you can have your own data set, or just use the empty car data set in built-in R, or from the ABD package, you can use the same lion data set that I'm using. Our goal is to predict the age of lions based on the pigmentation of proportion of pigmentation present on their nose using a linear model. So first of all, we load the data and then we fit the model. So to do that, you attach the ABD, you kind of prompt in the ABD package, and then attach the line noses data set, and then you fit the model. To fit a model, we have this LM function to fit a linear model, and then the summary, you can call the summary on the model to get the interpretation. So you can see here, the summary function provides a detailed information about the fitted model, including the estimates of beta 0 and beta 1. So beta 0 and beta 1 are basically uh, when the estimate, the intercept, is your beta 0, and beta 1 is the estimate for your explanatory variable, which is the proportion of black noses in this case. And it also gives us the standard error. Along with that, it gives the t-values, which you can again use to see, like for here, we have our degrees of freedom is 30. So you can again use that along with the t-value to find the p-value. However, it also shows you the p-value, so you don't need the table here. So you can see that the p-value is very less than 0.05, which again tells you that okay, this is statistically significant, that the proportion of black nose does help in predicting the age of lions. Um, so once you're done fitting your model, you need to check for your if your model assumptions hold true. And to check for the model assumption of this linear regression model, we can use again diagnostic plots. And to get a diagnostic plot, you basically run the plot function, and it will throw out four different types of plot which you can use for your analysis, for your interpretation. So basically, these four plot help us to check for linearity, homoscedasticity, independence of the error, and normality of the residual. So the first plot here, the residual versus fitted plot, helps us check the linearity and homoscedasticity assumption. So basically what we want to see is that the points are randomly scattered without any clear pattern. And the normal QQ plot, this helps us check the normality of the residual. So points should basically lie approximately on a straight line. And if you uh, plot the histogram of this residual, you should basically get a bell-shaped normal curve. Um, then we have the scale location and the spread. It's also called the spread location um, plot, which helps us check for the homoscedasticity assumption again. Uh, to this is kind of like a secondary confirmation to the homoscedasticity assumption. So basically what we want to see is a horizontal line with points equally spread across both sides. And then for this residual versus average plot, um, it helps us identify the influential observations, if there are any present in the data set, which might again skew your analysis to one side or the other if there are too many of them. So uh, this can also be done using the Cook's distance plot. So this is basically a Cook's distance, but you also get Cook's distance histogram sort of plots, which I'll come to in our later videos, which we can again use um, to identify influential variables. But as far as this plot is concerned, the points outside the Cook's distance line might be influential. So let's see how these play out in our for the residual versus fitted plot. You can see that there is no um, pattern in this dots, and you can see that the line that's drawn through is doesn't have a proper pattern. Or however, if you look at it in a general way, you can see that it's kind of decreasing. However, still the plots are quite randomly scattered, and it's good enough for our uh, linear model. And for the QQ residuals, you can see that most of the points fall along the line, which again tells you that the residuals are normally spread out. But there are certain variables which are, certain observations which are out of these line, and they show you uh, the numbers here 22, 27, and 30. It gives you the observation, the observation number, like what's the row of these observations, so that you can actually go back to your data set and then verify if there was some error made on your behalf, or is it just what it is. um, so now moving on to the scale location graph. um, Here again, to check for homoscedasticity, we just want to see a horizontal line with points equally spread. So you can see that there is a horizontal line and the points are equally spread out, but it could have been better. Like uh, the homoscedasticity um assumption could have been way more better if probably if there was a different model to fit. And now coming to the residual versus leverage plot, you can see that uh, there is this one point which is standardized residual if you check, um, and if you check the leverage, it is way above 0.5, so it's almost nearing 1. So these are this um, observation, along with even 27 for that matter, is quite high. um, and even 22, it's always on the negative side, it's quite low. So for a general understanding, you want your observation to fall between 1, -1 and 1. You don't want it to go way below or way above these marks, and when it does, this signifies that these observations are influential points which might again skew your analysis in one side or the other. So we can again now go ahead into multiple linear regression, but I'll just end the video for this one because it's quite long. And in the next lectures, we will actually use examples, real world examples, to model multiple linear regressions. So if you have any questions, feel free to put it on the chat box. Oh, sorry, not chat box. Feel free to put it in the comments. And I hope you enjoyed the video. If you did, make sure you spread it because it might help somebody else. And it will help me as well. Make sure you're subscribed so that you can keep a track of all the upcoming videos, and I'm putting out these videos in a very sequential manner so that one knows what to expect after one video, and it's not just haphazard that you have some really complex knowledge of some topic and but you lack the basic knowledge of one. So what I believe is that you need to go in a stepwise manner, get the basics out of the way, and then you can deal with the more complex concepts. So with that being said, I end this video, and thank you for watching.